Hello, everybody. Thought I'd make a quick video to go along with the homework 5 key. So here we are. I'll run with it. Um, hmm. Let me make sure everything's working just right. Um, just gonna pop over here. Yeah, that's what I like to see. Okay. Yeah. So just what it says. Here we go. Yeah, so when are you going to be roughly half or 50% chance of sharing a birthday with somebody in the class? About 23 students. You picked that up from the spreadsheet we made. That's all there is to it. Here, just kind of table it out. You know, number of birthdays in a certain month divided by number of months, and there you go. You got all your percentages. Yeah. Um, nothing intense about this problem. Let's see, we're converting from counts to fractions to decimals to percents. That's um, that's what this problem was for. Just make sure you guys can do that. Be comfortable doing that. Of course, this is posted on the PDF if you want to look at some details or get some numbers out of it. Okay. 45 presidents. If they're equal size, there's an equal chance of hitting each one. 1 in 45. According to Wikipedia, there's 45 presidents. Okay. So a little note here, I'm not adding a lot of context because I'm assuming you've read these problems and you're using this after you've gotten your first feedback back. So here's my list of probabilities. For this one, this idea that traveler's odds, that I kind of took as an example of how we could maybe do a modeling problem with it. So I did some research. Turns out that one of the bigger problems in luggage mismanagement is dirty barcode printers, and about 90% success rate is what they can expect because those barcode printers get dirty so fast. So a couple other things. You know, another quote from the article. This article I read, "Traveler's Odds" by Jeff Bailey, said that 8.69 in 1,000 bags are mishandled. So there are some probabilities to think about. So like, you know, that's about 10%. That's a little less than 10%. There you go. Different answer. So I stole this problem. So this is someone making a connecting flight, and the idea is if they make their connecting flight, does their luggage also? Slightly different problem. But I wanted to give one more example of given probabilities when probabilities aren't independent. And so I really do it to it here. I calculate a lot of different given probabilities, and I show you which ones are independent, which ones turn out to just be the probability of being lost, say, or having lost luggage, etc. Yeah, just read through that. Ask me questions about it if you need to, but I'm using that formula, you know, one probability of 1 given 2 is probability 1 and 2 divided by probability 2. You know, just applying that formula over and over again, kind of observing when it's equal to probability safe, when it's not, etc. Okay, number 12, 8.2. So here's an addition grid for 2 dice. If you're reading through the chapter, you might have seen this. They also do it for a cube, the sum of 3 dice. Yeah, so the idea is that we're looking for 7s and 11s. 2 ways to get 11, 6 ways to get 7, 8 options total out of 36 ways to roll 2 dice. 8 out of 36 is 22.2%. There we go. 8.2.24. Looks like that's also a birthday problem. Yeah, cool. Moving on. Yeah, what do we got going on here? Yeah. That event. 8.3.2. Man, I'll have to read what that problem is again. Oh yeah, this was like an event happening, not happening over and over and over and over again. You know, any given event not happening all year, etc. Just a whole bunch of independent and probabilities. So we're multiplying there. So this one is this was okay. You've rolled 3 heads. What's the probability of rolling 1 more? And I did the probability tree just to prove that the probability was independent. That getting 1 more heads is 50-50 no matter how many heads you've gotten, because coin flips are independent of each other. If you have an unfair coin, that means they're not independent, or ish. The idea is that they're not equally likely there. Anyway, so yeah, I did the whole thing and did the given probability formula, and eliminated things and did algebra, and it comes out to 1/2. So I proved it. I started from the general formula, and I showed that yes, given 3 heads, rolling or flipping 1 more head is still just 50%, 1/2 right here. All right. So that kind of shows you, you can always work backwards. Start with the general formula. If you come up with a simpler result, that's all good. Straightforward substitution problem here. I just did it. Yep. Okay. Let's see. What do we got here? There's a list of probabilities. Think about those. If you don't have those answers, think about why. Okay. 8.4.7. Okay. Oh, Apple battery pencil is low. Okay. Better get done with this quick. So I'm looking at this. Okay, so how many codes, right? 10 digits. We're picking 5 out of 10 digits. So, 10 to the 5th, 100,000 options. Now, 200 students will try. And this is where I'm talking about writing your assumptions down and criticizing them to yourself. Because now I'm going to say, okay, is it that 200 students all try a code and nobody's communicating? Or is it that 200 students are lined up and they're like crossing them off the list? Like, I tried this one, you try a different one, right? So there's 2 ways to go about this problem. So let's try the simple option first. Nobody's talking about which code they got. So they're all just looking for the 1 out of 100,000 option. And so you got 200 tries at 1 in 100,000 per each try. So that's a probability of 0.2%. Now, what if you are eliminating a possibility every time? I made a little spreadsheet for this, and basically what it comes down to is the first guy's got a 1 in 100,000 chance, second guy's got a 1 in 99,999 chance, and so on. So how do you just sum up all those probabilities, right? This guy gets it, or that guy gets it, or that guy gets it, on and on and on for 200. And if you do that, you get a probability of 0.200199%. So much bigger than 0.002. Yes, 0.002000199. Big deal. A few millionths more likely. Yeah, really glad I investigated that assumption and spent an extra 5 minutes there. Oh, what do we got going on here? You're picking 40 things. Oh, yeah, lottery. Okay, so the important things about this is the order of the numbers doesn't matter. So if you have the winning order, if you have the winning numbers, you have the winning numbers. So that means there's 6 times 5 times 4 times 3 times 2 times 1 ways, or either 720 ways to pick the winning number. And how many ways are there to pick 6 numbers out of 40 numbers? 40 times 39 times 38 times 30 times 36 35. Somewhere around 100,000 million billion, 2.7 billion options. 720 divided by a huge number is 0.00000026. Yeah, basically never, right? I think as one of these modeling problems we'll do, I'm going to actually think about this a little bit differently. Like, this is the chance of winning a lottery. So multiply that by your lottery winnings, and that's your expected earnings, right? Um, then multiply that by the number of times you play, and those are your expected lifetime earnings, right? Compare that to the expected lifetime earnings of, say, putting $1 away every week and then putting it into an annuity. It's always a better deal. Yeah, so statistically speaking, it's a better deal. Okay. 8.5 is a little trickier, I think. I think the rest of them are a little more straightforward, but this one's tricky. Or at least it was for me. Yeah, so here we go. So if player 2 decides to defend against strategy B, that's what the pink line represents. So, and this x-axis is the probability that player 1 uses strategy A, and this is the payout, right? So, what this line says is that if I'm using strategy B and getting a payout of 7 from the grid on 8.5.15, then there's 0% chance I use strategy A because I use strategy B, right? Same thing, 100% chance I used strategy A, but they were defending against B, so I got the $10 payout, right? And the intersection of those two lines is a third 8. There you go. The section on this is interesting, if you like football, and so on. It was kind of neat. It was worth a read anyway. Yeah. All right. Zooming in on the finish line here. Dinosaurs. I think it's no secret that I like dinosaurs. I was pleased that this problem was in the book. So you can kind of do this one with a sort of probability tree looking kind of thing. It's actually a proportion tree because they're determined. They're not probabilistic. They're determined proportions, but the communication is pretty good there. So yeah, you see you got 1,000 bones, split them into 3 categories. We got Juliasaurus, Noasaurus, and other. 50% of 1,000 is 500, etc. Then you take each of these sub-quantities, right? 0.5 or 5% are found with, what was it, Maxosaurus or something? And so on, yeah, so you get these splits. So then we look back up here, right? So what we have is that rows total up to the total in each category. Columns total up to the total, right? So we see that columns are numbers we had to calculate. You know, what's 95% of 500, etc. 30% of 150, so on, or 60% of 150, so on, so on. Yeah, so what we have here is that this is the expected distribution of dinosaur bones to be found if we found 1,000 of them. So what we do is, now that we have this expected distribution, we can compare this to actual bones found, right? The idea here is what is usual, what is unusual. Now we know what usually should happen. We're able to identify when a find we have is actually unusual. For example, what if we found 100 Juliasaurs that were found with a Maxosaur? We might want to investigate further. There might be something interesting going on there to be found. Okay. The last problem is a discussion problem, and I look forward to reading y'all's discussions. All right. That's all I've got for you today. Hope you have a wonderful day. I will see you guys in class. There it is.